In this script, we're gonna cover receive diversity. This is when the receiver has more than one receive antennas. So we can create diversity which can combat small scale fading. So let's look at our setup. We have a transmitter with only one transmit antennas. We have a receiver which has NR number of receive antennas. Okay, so you see multiple antennas here. Okay. So NR could be 2, could be 3, could be 4, could be 5. Okay. Now to analyze the performance of this system, we're gonna assume that the transmitter only send this simple symbol, which is binary phase shift keying or BPSK. So X is the transmitted symbol. So it's either gonna be 1 or 0, or in another word, we're gonna send this real symbol, which is square root of EB or minus square root of EB. Okay, so there are two choices. Now we're gonna do some. We're gonna assume certain channel models. The first assumption is this: we assume that the environment or the channel between the transmitter and receiver has with this rich scattering. So that means there are lots of objects in the paths. So signal will be reflected, and it's gonna be all coming to the receive antennas. And most importantly, there's no line of sight. Okay, and we're gonna assume that the system has very small bandwidth, so this is gonna be flat fading. Okay, so the link between the transmitter and the transmit antennas and the receive antennas only gonna be captured by one channel coefficients or one channel gains. So from the transmit antennas to the first receive antennas gonna be captured, the channel gains will be captured by H1. From the transmit antennas to the second receive antennas is gonna be H2, etc. to H subscript NR. Okay, so since this is gonna be rich scattering and there's no line of sight, so when the signal all coming to the receive antennas, it's gonna have this Gaussian distribution. So we assume that H1, H2 to HNR is complex Gaussian with mean 0 and variance 1. Okay. The second assumption that we're gonna make is the receive antennas are separated more than wavelength divided by 2. Okay. So all this all this receive antennas is gonna be separated more than 1/2 of the wavelength. So that means all the receive antennas are independent from one another. In another word, H1, H2 to HNR are independent. So all of these channel gains are behaving differently or not depending with one another. Okay, so that's gonna create diversity for us. Okay, now we're gonna look at what happened. So we are sending X right to the transmit antennas. This gonna get multiplied from different links, and then we're gonna get to all these receive antennas. Okay, so at the receiver, right, the receive vector, which consists of the receive symbol at first receive antenna, so that's gonna be y1. Second receive antenna, that's gonna be y2 to y subscript nr. Okay, so y1 is equal to h1 multiplied by x, y2 is equal to h2 multiplied by x to the last receive symbol, which is ynr, is hnr multiplied by x. So you see that we are sending the same transmitted symbol from one single transmitted antenna. So we can take out the x. Okay, so we have this vector which consists of h1 to hnr. So we're going to denote this as h with the underline. So this going to denote vector, right? So this vector has size of nr by 1, right? So remember the entries are independent complex Gaussians. Okay, so that's always a noise, right? So that's a noise at the receiver too. Now, how do we detect X, right? So we're gonna use match filter. So it's gonna match with this channel vector. So we take H and do conjugate, right? So this is complex conjugate transport, right? So complex conjugate and also transpose, right? Because when you multiply vector, the dimensions has to be compatible with one another, divided by the norm of the channel vector. Okay, so make sure that we normalize uh, the power at the receiver. Okay, so we take match filter multiply with the receive vector. Okay, so that means we take this multiply with this, and there's always a noise. Okay, so noise is complex Gaussian, means 0, and variance is n0. I'm sorry, I got this wrong. Okay. Okay, so let's multiply things out. So you see that this is H transport, complex conjugate and transport. This is vector H, right? So remember this is nr by 1. So this one is going to be 1 by nr. But once you multiply, you're going to get a number. So that number is going to be in the norm square, okay, divided by its norm. Okay, so you cancel one factor on the top, okay, and we're gonna take the real part, right? So we only, since we're doing BPSK, so our signal is only in the real dimension, so we don't need to worry about the imaginary dimension. So we take the real part of what we got after match filter. Okay, so this is already real, right? Remember, this is either square root of EB or minus square root of EB. Okay, so this is real number because it's the norm of the vector, plus we only take the real part of the noise, so we're gonna use W to denote that real part. So since it's only the real part, it's not gonna be complex anymore. It's gonna be Gaussian with mean 0, and the variance is divided by 2. Okay, because it's only half of the whole noise. Okay, so we're gonna need denote this with R, right? So once we get this R, it's we're gonna do some thresholding, right? Whether it's bigger or less than 0, and that's gonna be all at the output. It's gonna be all detected symbol, right? Okay, if it's bigger than 0, then it's we decode it as square root of EB. If it's less than 0, then it's minus square root of EB. Now you see, if you look at this final equation, you see we have transmitted symbol, right? We have noise, but this is extra, right? This is because of fading, right? Small scale fading, and because of that match filter. So you combine all those channel gains in the same, you first convert it into the same phase, right? And then add them, right? So they are adding in the same directions. Okay. Now, the performance will be determined by signal to noise ratio. That's signal power divided by noise. So signal power, that's this part, right? So we take it to power of 2, that's going to become power, right? So X square root of EB minus square root of EB, right? So you find the average is EB, okay? Channel vector raised to power of 2. Noise power is the noise variance, okay? So we have this. Okay. Now this looks very familiar, right? Because when we want to determine bit error rate, right? Since the noise is Gaussian, it's going to be Q function of square root of SINR. We already determined SINR, so I plug it in. Okay. So it's the Q function of square root of this channel vector, norm of the channel vector square, right? And multiply with 2EB over N0. So this, it's very familiar to you, right? Because that's the performance of bit error rate of additive white Gaussian noise. So the extra is this. So this gonna make signal to noise ratio to be very small. Okay. So this is random variable, right? So we need to do some averaging, right? So I take the averaging, so I take expectations. Now we are curious about this, right? This is gonna determine our performance. So we look at this term, okay? So it's a norm square. So we take each individual channel gain, right? Find the absolute value and raise to power of 2, right? We add them up, okay? Now let's go back to what we know, right? So if only one receive ethernaz, so basically this norm square is equal to one of the channel gain raised to power of 2, right? So remember earlier, right? We talked about this. This is exponential random variable. Okay, so what is exponential random variable? The PDF looks like this, right? With PDF, remember it's probability density functions, right? So it tells us how the probability, right, density, right? How does it distribute in terms of the values of x? So if we plot this, right? So this is the samples, right? It could be between 0 and infinity, only positive number, right? Because we taking the absolute value square, right? It cannot be negative, okay? And if you take plot e to the minus x, you get this graph. And you see that for this random variable, right? The density mostly sits here, right? Right? You see the function is high there. So most likely, the random variable will produce value that is even less than 1, right? So less than 1, right? It's gonna be rare that it's gonna be bigger than 1 because you see the density is very low. So that means signal to noise ratio will be affected, right? Because this number, right, will be less than 1. So it's gonna reduce to EB over N0. That's why our performance is very bad. Now what happens if the number of received etherna is bigger than 1? So now the norm square becomes the sum of many terms, right? It's all positive and you add them together. So this is going to be another random variable. This is the sum of independent exponential random variable. And you learn from previous classes that the sum of random variable, it's not easy, right? It can be another random variable. It turns out the sum of exponential random variables become what we call chi-square random variable. Okay, so what is the PDF of this chi-square random variable? Okay, so it looks something like this. 1 over nr minus 1 factorial, right? Remember nr is the number of received ethernaz. X raised to power of nr minus 1 multiplied with e to the power of minus x. So x only going to be bigger than 0. Okay. Now let's plot this. Okay. So first, if nr is small, right? This is the graph of the PDF. You see that it's shifted away from 0, right? It's going in this direction. So that means it's likely that the value of the random variable going to be close to 1 or even bigger than 1. Now, if nr is bigger, the PDF is shifted, right? Shifted to the right, right? And if nr is very big, it's gonna even shift it more to the right. So that means it's gonna produce the number that is away from 1, bigger than 1 even. Okay, so that's good, right? So that's why when we have multiple receive ethernaz, our performance is better. Now, if we use all this and evaluate bit error rate, okay, then you can analyze bit error rate, and it turns out if you only want the approximation, right, when EB over N naught is very large, right, we can approximate bit error rate as equal to 1 over EB over N naught raised to power of NR. So this is important. This power is important, right? Because if NR is big, it's gonna make the denominator even bigger and bit error rate gonna be even smaller. So remember, NR is what? It's the number of received antennas. And the bigger the number is, bit error rate, it's gonna be even smaller, or the performance is gonna be even better. We also gonna call this NR diversity order. Okay, so it tells us how much diversity this transmission scheme has, right? So it equal to the number of receive antennas. Now, remember, if NR is equal to 1, if we only have one receive antennas, then it's going back to 1 over EB over N naught, which is very bad, right? We do some simulations and we talk about this before. Okay, so this is about receive diversity.